So let's get to the analysis part of it. And what we want to do now is develop equations that are going to help us kind of just solve the energy part of this, like how much is going from one fluid stream to the other, how do we predict the temperatures as a function of position, how do we predict the rates of heat transfer. All right, so let's look at our heat exchanger. Now we've got this control volume I've drawn out. By the way, aside, I posted 2 lectures worth of blank slides. You might notice for the rest of the semester I'm going to be posting lectures kind of a couple at a time. You may guess that that's because I'm about a couple of lectures ahead of where I am right now. So just be aware that if you don't see anything right now, the notes will show up hopefully at least the day before. Okay, so we've got this control volume. What we're going to do is just do an energy balance kind of on the whole thing. So let's kind of keep track of what's coming in, what's leaving, and then we'll see where we're going with it. So as I've got drawn here some hints of kind of where we want to start. Let's look at the flow coming in and the flow leaving, and then what's being transferred. So coming in, let's call this stream up here the hot fluid stream, and let's call this the cold fluid stream. All right, so going into the top, we have some mass flow. That's m dot h. We have some either temperature or more appropriately, I guess we could say enthalpy. So let's do this in terms of enthalpy first, and then we'll convert it to temperature. So m dot h, IH, right, that's the enthalpy, and that's the enthalpy going in, so it's IH in. Let's assume that mass is, there's no loss of mass in the system, that what goes in goes out. So then on the right side we have m dot h, and we have IH out. Okay, this is not yet like a differential analysis. We're just trying to do energy balances on the entire fluid all at once. Okay, so we're not doing like the x plus dx thing. Okay, on the other side, we've got the cold flow, that is m dot c, IC in down here, m dot c, IC out over here. And then we have some heat flow, Q dot, we'll call it. Q dot is the accumulated heat flow from the entire length of this system. So then doing an energy balance on the entire thing, we have in plus m dot c, IC in minus m dot h, m dot h, IH out, minus m dot c, IC out, equals 0, right? It's just in minus out. Okay, so that's the overall energy balance. If we make this assumption now that it's incompressible flow, that means we can say enthalpy is basically C specific heat times some temperature, I suppose minus like a reference temperature, something like that. We can then rewrite this as follows. It's just m dot h times specific heat CH times TH in minus TH out. And hopefully everybody sees where that comes from. CH, so we'll be careful. CH is the specific heat of the hot fluid. And then we're just doing that energy balance kind of on that top part, grouping things together. And then that's equal to m dot c, CC, TC, let's see, what, TC out minus TC in. All right, so this enthalpy statement is directly related or directly produces the temperature statement. We're just substituting the specific heat times temperature. So we have to preserve like the signs of in versus out, which is why on the left here we have in minus out, and on the right we have out minus in. But if you actually think about it like intuitively, we would expect like some positive amount of heat is coming out of the hot fluid, and that same positive amount of heat is going into the cold fluid. So they should be like opposite in sign, right? Okay, so that's just kind of the overall energy balance, and then we'll use this to start developing a system of equations we can use to solve for temperatures and stuff. Okay, so some definitions now. Stuff that we're going to need to actually characterize this. First thing is you're going to see this product m dot times c a lot of times. Like it shows up pretty much everywhere. The units on this are watts per Kelvin. All right, so it's actually the same units as the thermal resistance, but it's the inverse. So kind of interesting. And it's called the capacitance rate. Capacitance rate. What it is, it's the product of the mass flow times the specific heat. So it's basically a measure of how much energy a particular fluid can take with it. Right? It's the capacitance rate of the fluid. All right, so that's one definition. So we can just substitute that back in and say now Q dot is equal to m dot times c, so that's just c dot. Let's say c dot h times th in minus th out is equal to c dot c, tc out minus tc in. Okay, just changing the equation we just developed. All right, another definition. We are going to be talking about the performance of these heat exchangers. The performance depends on the design, which dictates like the thermal resistance between two fluids. So in your homework for this week, you're just looking at like the total resistance between the fluid inside the tube and the lake. So it's kind of like a heat exchanger. That same idea applies here where we're looking, what we want to do is look at the total resistance between, let's say like fluid going through this inner tube. I don't know if you can, what I drew here is like if you take a tube inside another tube and cut it in half and look at it from the side. So improvement needed on drawing. But what it's showing is hot fluid on the inner tube, cold fluid going the other way on the outer tube. And the fact that you have now like a series of resistances between the two fluid streams. So you have like the convection on the inner wall, you have convection on the outer wall. Right? So where I'm going with this is we need to characterize performance of this. So we need some way of measuring like that total resistance, the total impedance to heat flow from one stream to another. So there's a term for that. I'm giving you definitions. This term, the symbol for it is UA. That is one symbol, sort of. UA is equal to 1 over R total. All right, so UA is called conductance. Okay, so we have capacitance rate, we have conductance. The conductance of the heat exchanger is, well, as the formula says, it's a measure of how well heat moves from one fluid stream to the other. So as the resistance goes up, conductance goes down. So if you want like a good heat exchanger, you want good conductance, you want high conductance. Where it actually comes from is this thing U is effectively like a total heat transfer coefficient, or like an effective heat transfer coefficient. So think of it like H bar A, right? Like for convection, but U includes everything in the resistance network. A is the area that's available for or the area of like the contact between the two fluids. Okay, so that's conductance. So like I said, high UA is a good heat exchanger. All right, this R total, so let's deal with that. R total, for this example I've put up here, that includes our convection, our convection on the hot side. It includes our conduction. It includes our convection on the cold side. If we were to actually write out the formula for this, it would be like this. So convection would be 1 over, let's say, H bar on the hot side times the area. So that'd be pi d in times L. Then my conduction would be the conduction resistance for a cylinder, which is Ln d out over d in. over 2 pi K, let's say K of the tube. So let me just be careful there, right? Conduction property of the tube times L. And then the last one is, let's see, 1 over H bar C pi D out times L. So that would be how I would actually evaluate the total resistance here. Okay, and then I take 1 over that value, that's my conductance. All right, questions on this? What we're doing is we are saying two things are true. One, if I draw a control volume around the entire device, right, then everything going in and everything going out has to be conserved. So that's where that top equation comes from. Where the other equation comes from, the other one, I mean, I kind of snuck this in here, but this here, this is both equal to what's happening on the hot side and what's happening on the cold side separately, right? Like it's the same heat that's being transferred. So we happen to like write out this Q dot, like, because we know it's occurring, and then we can do a separate one for the top and a separate one for the bottom, and they're equal to each other.